And last but not the least, we're going to study transformers. What's a transformer? I'm sure you heard about this term before. A transformer is a device which can upgrade and downgrade the values of AC voltages. Okay, it only works for AC, but it can turn, for example, 110 volts to 12 volts. That's called a step-down transformer. You can also turn backwards. You can turn the 12 volts to 110 volts, for example. It's called step-up transformer. Okay, so how do transformers work, and why do we need transformers? First of all, why do we need transformers? Why do we have to use different voltages? Okay, now there are two major reasons. Okay, at least two major reasons. One is, you know, the powers are transmitted from a power plant, which is usually located in a remote area, and it has to go over long distance to reach a major city, right? And we don't want a lot of power to be wasted as heat on the long transmission lines. So the way we resolve that problem, we want to carry a certain amount of power, yet we want to minimize energy lost, is to carry the signal at an extremely high voltage, say 110,000 volts. Okay, why? Because that way you only need a tiny bit of current in order to transmit a certain same amount of power. Remember, power is equals to I times V, right? You put a very, very high V, so I can be very, very small, and you only need to drive a very, very small current over the transmission line. Therefore, the power generated, which is I squared times R, R being the resistance of the transmission line, will be relatively low. Okay, that means it takes, you know, these long range power transmission takes extremely high voltage. And yet, when that signal goes to actual households, okay, you cannot plug, you know, a device into a power socket that says 110,000 volts, right? It is too dangerous, and also will fry the electronic equipment. So what we need to do then is we need to downgrade. We need to downgrade the voltage. We have to take it from 110,000 volts to something manageable, say 110 volts. Okay, so you see, this is when we need what's called a transformer. As a matter of fact, this process of downgrading a power line voltage to something that we can use at household level is a multi-stage process. Okay, when this when the transmission line carrying extremely high voltage carries energy into the city, well, it first has to go through a power station. That's a professional station in which a transformer group will downgrade extremely high voltages to maybe a few thousand volts, and then that voltage will then be distributed through a certain neighborhood. And then before it enters your house, you could get a transformer, which is probably the size of a table instead of the size of a building, which will convert the higher voltage to something around 110, so each house can then take it. That transformer, which is the size of a table, can probably take care of, say, a city block. Okay, so it's a multi-stage process. And finally, when you plug in a laser disc player or a television, whatever, into the power outlet, did you know that most small electronics, okay, such as a CD player and MP3, whatever, your cell phone charger, they actually require much lower voltage, okay, say 6 volts, 9 volts, 20 volts, or whatever. So you have to take 110 volts, downgrade them even further, so that these electronic devices won't be fried. So the when you plug something like that into a power outlet, okay, into a wall outlet, you notice that you do not simply get a simple cord. Rather, you have this little black box, right? This little black box. What's inside? That, in fact, is also a transformer. Okay, it's also a transformer. It takes 110 volts and downgrade it to, say, 9 volts or 20 volts or whatever is required by this piece of electronics. So that is one. These are actually two reasons that I just mentioned. One is long distance transmission. The other is the operation of electronic devices, which take typically much lower voltage than the power outlet. So we certainly do need transformers. Okay, so how do transformers work? How do transformers work? Well, inside each transformer, we have something similar. Typically, you would have a piece of soft iron. We use iron to enhance magnetic fields, okay, because these are ferromagnetic material. So what you do is you have an input signal at a certain voltage. We call it primary or input coil, okay. It comes in via this solenoid, okay. So you wrap it around one side of the soft iron core like this. Okay, so again, this is V in. Okay, this is the input signal, V in. Meanwhile, the other side is called the secondary or output side. We hook up to another solenoid. This solenoid has different number of turns. Okay, different number of turns. Okay, on the primary side, the number of turns is N1. The secondary side, number of turns is N2. Now, because of the soft iron we use, the magnetic field lines are more or less trapped inside, and ideally, we say the same number of magnetic field lines will go through both of them. Okay, we'll go through both of them, like this. So you see, if this is an AC signal, then it's going to vary over time, and therefore it's going to cause a variable magnetic flux going through the primary coil, and then the same magnetic flux will be felt on the secondary coil. Okay, that is going to cause an induced EMF over the secondary coil, and that is your output. That is your output. Okay, so V out is right here. So what we really care about is the ratio of V out versus V in, right? And then since we assume the same amount of magnetic flux will pass through both coils, then it's quite simple to calculate. V out, for example, is just N2 times d phi by dt, and V in is just N1 times d phi by dt. If you cross out the two d phi by dt's, you get simply N2 over N1. So you see, it is very easy in principle to get a step-up transformer. All we have to do is to make sure N2 is greater than N1, then the ratio is greater than 1, V out is greater than V in. That's a step-up transformer. And to get a step-down transformer, you just do something as we drew here. You put less number of coils here on the secondary versus the primary coil, and then N2 is less than N1, you get V out less than V in. That's how you go for a step-down transformer. Okay, now from the conservation of energy, we know that you cannot get energy out of nothing. So ideally, even if there is no thermal loss, no loss due to resistance or whatever, the amount of current that you get here, I1, and the amount of current you get there, I2, should be related like this. I1 V in equals I2 V out. Okay, so if you go from a low voltage to a very high voltage, it doesn't mean you have generated energy out of nothing, because you will get a smaller current in return, so that the product of I times V will at the very best match on the secondary side versus the primary side, assuming there is no thermal loss due to overheating, due to the fact that the soft iron might heat up a little bit, which always happens. But this is the ideal case. Okay, so there is no violation of the conservation of energy. A higher voltage requires a lower current to keep the power in check. So that's the basic idea of a transformer.